Okay, good evening. Assalamu alaikum. We will start properties of matter theory classes from today. Properties of matter has three main subunits. One is elasticity, second one is viscosity, third one is uh, surface tension. First one, today we are going to study is elasticity. Okay, elasticity is there for objects that are elastic. Okay, so what do you mean by elastic? Do you know the definition for the term elastic? In your mechanics, you have studied something called force constant or spring constant, right? In your mechanics, actually, when you study about energies, you had two types of mechanical energies. One is kinetic energy, second one is potential energy. Potential energy is of two types. One is gravitational potential energy, the other one is elastic potential energy. So when you studied about elastic potential energy, you studied about elastic objects. So by definition, elastic objects must possess three main properties. Okay. First, when you apply a force to them, they have to undergo deformation. When an external force is applied. And it will always exert a resistance for deformation. Okay, for example, take a small piece of rubber band. You are pulling it, let's say you are pulling it. So the rubber band will pull you in the opposite direction. When you pull the rubber band in the right side, it will pull you to the left side. So that is giving some kind of resistance. Once the force is released, it will return to the original shape. It will return to the original shape. So this is what you call elastic objects. Now, some will deform, but will not show any resistance or will not come to the original shape. For example, clay. Clay you used to play with in the childhood, and then you can also say chewing gum that has been chewed for some time. So you can just pull it, it will just deform, but it will not return to the original position. Okay, so those are not elastic. Do you know the name for these kind of property? They undergo change, but they don't return. Why? What? Kind of opposite of elastic? Don't know? It's called plastic. Okay. Give me 1 second. Hello. Walaikum Salam. All right. So here, so you have elastic and plastic. So here we will study only about elastic objects, right? Okay. And mainly we study about forces that are applied in a longitudinal fashion. Okay. you can apply forces from all the directions and compress something. You can apply force tangentially and create tangential deformation. But here we only study about longitudinal. Okay, the example is our usual spring, for example, or a metal. Metals have something called a property called ductility, right? So when they are ductile, they will usually be elastic. But it's not a very evident elastic property like in your rubber band. It's very subtle. Only small amounts of extension or compressions will be there in metals. Okay. Now look at this. This is a piece of metal. I'm going to give a small force. We will just increase the thickness, right? I'm going to give a force. So when I give this force, let's say the metal increases in size, length, okay, to be precise. Initial length is L. Let's say when I pull it with a force F, it undergoes an extension of E. When it is elastic, there is a law that says F is directly proportional to the extension or compression. What is this law called? Anybody?
Hooke's.
Yeah, you can't forget it. Hooke's law. So he says the extension or compression will be directly proportional to F within proportionality limit. Within proportionality limit. Okay. So it's proportional until it is reached the proportionality limit. After that, the equation is not valid. Then you make it into an equation. F is equal to Ke. K is a constant. You call it a force constant, or if for springs, you call it a spring constant. Spring constant. This is a constant, but it depends on some of the things. Does it depend on the length of this? Huh? Students, does it depend on the length of this? Yes.
Yes.
Does it depend on the area of cross
Yes.
section?
Yes.
Very good. A. Does it depend on the material that it is made up of? Yes. So you can't call this K a constant for this material. It's a constant for the particular object of that length and area of cross section. You can't say that it is specific for a substance. It's not specific for a substance. It depends on the dimensions L and A. So Hooke's law just gives us an idea about the extension. And you can also derive an equation for the energy stored, right? That was the main objective when we studied energy. So, you know, when the force is applied, should be in the y-axis. E should be in the x-axis. Okay. An area that it makes with the x-axis will give you the energy stored. Okay. So that is your elastic potential energy EP equal to area of the triangle half into base. We'll say E, force perpendicular height will say F. So elastic potential energy is equal to half Fe. So instead of F, you can put Ke. Okay. F is equal to Ke. So therefore, you can say EP is equal to half E into KE. So it gives you another equation, half KE squared. Okay. Again, if you put E is equal to F over K, then you obtain EP is equal to half. Instead of E, we are going to put F over K into F. Alrighty. So EP is equal to half F squared over K. All three equations will come in handy according to how they give you the question. Okay. So this is what you studied in mechanics. Okay, this is what you studied in mechanics. So now just think, okay, now just think, why does it undergo, why is it elastic? What actually happens at the molecular levels? Do you know? Anybody? If you see the molecular arrangement of the metals, okay, so there are atoms like this, no? Atoms, oh, what do you call? Basic structural unit, whatever you are going to call it. So they are strongly bound to each other. So when you apply a force, they undergo extension. Because when you apply a force, the intermolecular space will slightly increase. Okay. When the intermolecular forces slightly increase, it will produce a resultant extension, cumulative extension. Okay, now see, when you have more molecules, okay, now this is what I explained you initially. So now when they have more molecules, you will have more intermolecular space, isn't it? So when every space increases, here the number of space is high. So let's say every space increased by some nanometer. Okay, so when you increase the number of spaces, what will happen to the resultant extension? Same force applied for both, which will produce great extension compared to E. E1 will be Come on, it's a simple question. Tell me, greater or smaller? When you have more intermolecular spaces, more
Greater.
Okay. Yes, more intermolecular space increasing the distance. Therefore, the cumulative means addition of all those will be greater than the first instance. So therefore, E1 is greater than E. Okay, now imagine. I am going to increase the area without increasing the length. Now, when I apply same force, what do you think? Here the extension is E2. What do you think? Compared to E, will E2 be greater or smaller?
Smaller.
Why is that?
Like
So whatever the what?
Like force is needed for many molecules here to increase the.
Yeah, actually the force distributes for the layers. When you give F here, it will be used for this layer, this layer, and this layer. So it's kind of split into three, F by 3, F by 3, F by 3, acting on three layers. Here also the same distribution, but here the number of layers is high. So it will be like F by 5, F by 5, F by 5. Here I have shown 5 layers. So it will be distributing itself one fifth of the total force, here 1/3. So therefore, every layer is going to get smaller force. So their extension will be smaller. Okay. So this is how the length and the area of cross section affect the total extension. So therefore, they decided to talk about extension and the force relative to the length and the area. Okay, so extension, whatever the extension comes, they wanted to give it for unit length. Okay, so they talked about, because when you are changing the length, actually the extension changes. Okay, so therefore they want to talk about for a unit length. Similarly, when you change the area of cross section, the force. So they don't just discuss the force anymore, they discuss the force per area. Okay, force per the area. So we are making these dimensions not affecting the calculation. When you say for unit, okay, it's not going to affect, right? Okay. Now comes the parameter E by L and F over A. We talk about the extension per length. So that is strain. And force per area, that's called stress. Okay, this is applied only when the force is longitudinal. Okay, I already told about this, right? Let's say that there is a box. If I apply a force like this, it will be longitudinal deformation. But if I attach this and give a force in this direction, it will undergo some deformation like this. So this is like tangential, it's going to a side. So, okay, that's called shear. You will see shear stress and shear strain there. Similarly, for a bag of gas, you can apply force from all the direction. Okay, actually the pressure. To increase the pressure, it will become smaller in size. This one and this one are not tangent, not longitudinal. This one is tangential. This one is bulk, volumetric. Okay, so it will lead to some other formulas. We don't study those. Okay, it will lead to shear modulus, bulk modulus, etc. We only study about giving forces longitudinally along the length. Okay, so therefore these are out of discussion. Okay, so when we talk about longitudinal, it's mainly tension. Okay, tension. So we call it tensile stress and tensile strain. Okay, always you had read that. Okay, tensile and tensile strain. Okay, now I will write some equations. So look at the previous example. Okay, we took the. So say that this has an initial length L, area of cross section A, and of course F is applied. It undergoes a small extension of E. Okay, initial length is L, not final length. Okay, always remember whatever that comes in our equation is initial parameters. Okay, so here tensile stress is F over A, tensile strain is what? E over L. Okay, give me 1 second. Okay, tensile stress and tensile strain are expressed like that. Now, the ratio of the tensile stress and tensile strain is called Young's modulus. That's equal to F over A divided by E over L. Usually for Young's modulus, what we use is capital E. Sometimes they use Y, capital Y. But E is more common, so we can write E is equal to F. If you rearrange this, you can write FL over AE. Okay. Now, by talking about the force and the extension per unit area and length, you have removed the factors length and area from here. Do you understand? Huh? Do you understand what I'm telling?
Yes.
Yes. Like for example, if you talk about like total amount of water vapor in a room, if you change the volume of the room, or if you connect it to another room, it's going to be different, right? And when you talk about the atmosphere, you can't actually calculate the total amount of vapor and all. So in those instances, you go for absolute humidity, which is the mass of the water vapor in a unit volume. So similarly, here you have talked about the stress and the strain in terms of unit area, force and the extension with in terms of unit area and length. So therefore, you have removed those factors. So here, this ratio is actually unique for a substance. It is unique for a substance. Okay. This ratio is unique for the substance. Now, if you make this F your subject, what you get is E AE over L. You remember this equation also, F is equal to KE. Both equations are same. Both can be written for the same object. Now, what do you see? F is there in both. E is there. Here K is there, but here instead of K, you have a equation EA over L. So actually, K is EA over L. Force constant is actually EA over L. We told about the factors affecting K. We told A effects, L effects, and the property, the substance, nature of the substance effects. So all three are included in this. So this is the exact equation for K. So now you know what will happen to K when you change A or L or E. Okay, this is a question case. Right? Have you tried your past paper? This 2025? You haven't. You are not interested. Or what? Tell me that you're done. Now here, third question. A spring mass system oscillates with period t. If the length of the spring is halved and the mass is reduced to half of its initial mass, what will be the new period? So you guys know the equation for the period, right? What's the equation? T is equal to 2 pi square root m over k. So people thought it is independent of the length. And even some of the bright students didn't get it correctly because they thought K will be constant. But when the spring is halved, what will happen to K? Tell me. L is halved divided by 2. So,
A
quick. Yeah, it doubles. It doubles the K, and then already the mass is reduced to half. So here 2, due to mass in the denominator, there will be 2. So 2 into 2 square root of that will be 2. So T by 2 is the answer. But if you got only the mass, it will be answer 2. So you have to be careful, okay? That's what I say. Before you go to the exam, you go with clear, solid theory so that you don't miss anything. Okay. This question came even in 2004, 2005 or something. There was a statement question about the factors affecting the K. So you won't miss it if you have done the past papers properly. Okay, it's just that that student got 48 or something, and one of the questions that he missed was question number 3. Okay, alrighty. So where are we? So we have studied about Young's modulus. Okay, now you have to just do questions from this. This is pretty much all the theory you need to know. Okay, there is nothing more. There is, but they don't come to the questions. So this is pretty much you will need to do essay questions. But if you want to go into more theory, we will discuss. I will discuss anyway. I'm just telling that this is the most important part that you need to understand. Now tell me the units and dimensions of Young's modulus. Unit?
Newton minus.
Yeah, actually, this strain is unitless, dimensionless. Why is that? Because extension is measured in meters or length. This is also a length measured in meters, so it will not have a dimension or unit. But this one, force divided by area, will have. So unit will be, this doesn't have unit, so units of Young's modulus will be units of stress. So it will be Newton meter minus 2. What is the dimensions?
ml minus 1, t minus 2.
ml minus 1, t minus 2. So it's ml t minus 2 for force divided by area squared. Sorry, L squared. So therefore it will be ml minus 1, t minus 2. Okay? Okay. Can you measure Young's modulus in Pascal? Yeah, you can. Okay, Young's modulus can be measured in Pascals. Okay. Now, if you try to draw a curve for stress against strain, okay, what will it look like? So initially, it will be proportionate until it reaches a point called proportionality limit. Okay. So they will usually name it P. Okay. And then the curve will start to appear. It will curves towards the strain side. Okay, not like this, because usually for metals, usually we draw, this is the graph. It will curve like slightly towards the horizontal. And then the molecules undergo permanent deformation. The elasticity is lost because the bonds, they start to break, some of them. So the materials start to flow, they say. The molecules will above one another, they will kind of develop fluidity. They undergo permanent deformity. So elastic property will become plastic at that point. Okay. Before that stage, the elasticity is preserved. So even though it's not proportional, for some time the elasticity is preserved. So up to that point, you call it a elastic limit. Beyond that, it's plastic. No more elastic. Okay, I'll tell again. So the object that has elastic property will undergo proportional deformation until proportionality limit. After that, it will be elastic but not proportional, and there is a limit for that also, elastic limit. And beyond that, it will undergo permanent deformation. Plastic property will be gained. Okay, so at that point, it will kind of come like this. Okay, we will name it Y. It's called yield point. That's the maximum plastic deformation happens. And after that, for some time, it will undergo plastic deformation. And finally, it will come to a position, okay, break point. Okay, breaking point. So at that point, the discontinuity happens. It undergoes fracture. It's no longer a continuous piece of metal. Now it is broken. And this is the maximum stress. Okay, it's the maximum stress. Once it is reaches, automatically it runs to breaking point. Okay. So breaking point is the point where the object is no longer there. Okay. So this point is called what will we name it? We will name it X. No? It's called break. It's about to break. So at that point, there is maximum stress. And automatically it will break. So therefore, it's called breaking stress. Once it is achieved, the object breaks. So during the breaking, because the transmission of force is affected, so therefore the stress suddenly drops. Okay, so this is a small area, you don't need to worry about it. Okay, so now again you will revise. This is the point at which the proportionality is preserved. After that, the proportionality is no longer there, but elastic property will be there. No permanent deformity occurs. But elastic limit is there. After that, permanent deformity starts. So at this point, there will be plastic deformation maximum. And from Y to X, it will be plastic. Okay, no elastic deformity. It's plastic deformity. If you release the force, for example, here, it will come back, but not to the original position. Okay. It will be having a permanently different initial position. Okay. And then maximum stress, breaking stress comes. And after that, automatically, it will undergo something called necking. Neck is a slender part, right? So when a force is applied, it will initially become like this because it looks like neck. So it's called necking. And after that, it breaks. Okay. Do you understand? Proportionality limit, elastic limit, yield point, breaking stress, breaking point. I will not give you notes, but I'll send you a PDF. Okay. Now, what do you think is given by the gradient of the graph until P? Anybody?
Young's modulus.
Exactly. Because it's stress divided by strain. So it's Young's modulus. What do you think will be given by the area under the graph?
Energy stored per unit volume.
Energy stored. You mean the total energy or what? Hmm.
Like total energy, like per unit volume.
Yeah, so it's not total, it's per unit volume, right? So it's the energy, elastic potential energy per unit volume. So actually, it's like this, okay? Half into the area is actually what? Half into whatever the stress into whatever the strain at that point. So it is similar to half FE, but divided by what? AL. Area into length is what? Volume. In your Hooke's law, the graph had only F and E. That is the total energy. So here the total energy is there, but it's divided by AL. So that tells us, because AL is volume, what we are talking about is the energy stored per unit volume. Any questions there? No questions there? Okay, so now you know this graph also. You have finished 90% of the syllabus now for elasticity. There is only a little bit of theory. Now, yeah. Now consider. So now we are going to. You know about thermal expansion, right? You have studied heat. No? Have you studied heat?
Yes, sir.
Hmm. So when you heat something, oh sorry, when you heat something, one of the thermal effects, one of the effects of heat is expansion. Can you explain me how it happens? When you heat something, how does it expand? Don't know?
Kinetic energy of molecule increase. So
What? Yeah, yeah, correct. So
yeah,
the vibrations increase. Yeah,
yeah, yeah. So the distance, like in the ends, the distance increases in all over.
you are saying in the ends, and also you're saying all over. Which one you're going for?
In all over the distance increases, like yeah,
Yes. So everywhere the intermolecular distance increases. So that produces a summation. Addition of all those will give you a small extension. So that is what you call thermal expansion. When you increase the temperature, they dance. Okay, they're dancing, no? So when they dance, when the temperature increases, the amplitude increases for the vibrations. So therefore, they have to move away from each other because they are moving to a greater range. So every intermolecular distance widens. Then that produces a delta L. So here it's not force, here it is kinetic energy or motion that produces expansion. They say that expansion is directly proportional to initial length because when you have more length, it's more molecules, more intermolecular distance, more expansion, and also directly proportional to delta theta. And when you insert a constant, you get an equation. What is this constant called?
Linear expansivity coefficient.
Linear expansivity. No? Expansivity. Okay, guys, it is coefficient of linear expansion also, or linear expansivity, alpha. Alrighty. Okay, now now you are going to create a fight between thermal expansion and mechanical compression. How do you create a fight? Say that there are two rigid walls. The vertical ones, those are two walls. They will never move. They are rigid. They are fixed. Now you are attaching a rod of length L between those two rigid walls. Okay. Now you are heating it. You are giving some heat. Now, will the kinetic energy of the molecules increase here? Hmm.
Yes.
Yes. But will it expand?
No. No.
Yes, because it is attached between two rigid walls. So walls will not allow expansion. So there will be thermal, what do you call it? Thermal effect is there. The molecules will increase in motion, amplitude, but they can't move away from each other because they are kept between two rigid walls. So how is that motion, sorry, the displacement of the molecule stopped? That is by applying mechanical force. This wall creates mechanical force. The wall will compress with the force F, and that will produce a mechanical compression that will equal the thermal expansion. Okay, so you know thermal expansion delta L is equal to L alpha theta. And you know the expansion by mechanical force, you have to start from this equation. E is equal to FL over AE. Here for expansion, we are using delta L. So I will avoid E, and instead of E, I will put delta L. Okay? You understand? Now both delta L's are same. No? Yeah? So you have to write here thermal expansion. This is mechanical compression. The thermal expansion is equal to, so it's not happening. Thermal expansion is not happening. because it's cancelled by mechanical compression. From this equation, you can have del to FL over A capital E. When you equal these two, L alpha theta is equal to FL over A, isn't it? You can chop the L's. So now you can derive an equation for force generated. Okay. Now listen to me carefully. This is the force applied on this. Here F is applied, here F is applied. So what is the total force acting on this? Okay, I will confuse you like that. Okay, it's F. Okay, it's like you are giving a force T, giving a force T. What is the tension? It's T. Okay, those two don't cancel. The force is actually it's everywhere along the length. The force is F. This wall will be applying F to this side. This wall will be applying F to this side. Everywhere the compressive force is F. Okay, you understand? So you don't cancel this. Some students say, okay, F from this side and F from this side cancels. So therefore it's 0. That's the big misconception. Okay. That's the thing. Now, do you have any questions? So I have questions for you in the tute. Okay. You need to do and come to the next class then. Can you do more? This is the note. I'm keeping the note. Okay. So first, it explains about the definition of elastic object. And I have differentiated elastic versus plastic, and types of deformation. Tensile deformation, it's longitudinally. Bulk deformation, it's to the volume. Shear deformation is tangential. Okay, then tensile stress and strain. Some people use for stress sigma and strain epsilon, but in our syllabus, we don't usually use. But it's okay if you are using. So I have defined, and then I have revised a little bit about Hooke's law. And here I have drawn a graph. Here you have extension, here you have force. When you change the axis, remember the graph will be like this, okay? And then I introduce you Young's modulus, and I give you an example question. And then I explain about this graph, and then I explain about this thermal stress. And then to feed your appetite for questions, I have given you 18 questions. Is it okay? I think there are answers also. There can be some typing mistakes, okay? But most of the questions are correct. Okay, you try to do. And then finally, I have differentiated ductility and brittleness. Okay. Brittle materials, they will also have a graph. When you apply a force, the graph is very small. They undergo a little deformation and then they break. The break point is reached very fast. Okay, because of the smaller graphs, the energy they store is very small. Okay, yeah, that's it. Do you have any questions? We have studied elasticity. We have to do some practice questions in past papers. Any questions? Okay, so when you study the theory, remember when you are able to talk about all the theory, like I did when I did the class, until you talk the theory like that, your study is not complete. Okay, remember that. Thank you.